If the all-important sun heats the ground, which heats the air to make all our thermals, then we obviously fly our fastest and biggest tasks on blue days. Not so, Moriarty. So it's obviously not just the sun then. Want to be a member of the Been About a Bit club? Introduce your name on the ladder, especially in a club glider. Get the optional guidance for glider pilot self-study. This book is the foundation notes for any AIM Higher course. Summary. String theory. Do thermals rotate? Feel the invisible sync flows. String theory. Atkinson's string theory. Approaching a thermal, you will first experience the downdraft, turbulence, then the speed increase, then the lift. The speed increase will also be detected on the variometer in the total energy system as a climb. Do not be fooled, you are not climbing. If you don't hit the thermal head on, then you will feel the wing lift, perhaps the aileron twitch, or better, see the string indicating a brief side slip, i.e. at the moment the string is blown away from the thermal center due to the horizontal gust, it is time to roll with full aileron and rudder. The bigger the gust, the stronger and tighter will be the requirement to turn. Ignoring mechanical turbulence. All conflicts between rising and descending air generate a horizontal gust. For us, this is always from the lift to the sink. You may not encounter lift at all, but the string may still deflect even in a heavy sink. Turn hard but roll out after 90 degrees. If you do not connect within 6 seconds, move on. Of course, string theory only works when you are approaching and adjacent to the core at an angle and in the upper half of the vortex. In other words, not head on, not too far abeam, nor too far below the top of the vortex. More on string theory and position, speed, mass. Placing the string further forward on the canopy usually makes it more sensitive. Adjusting mass to a glider adjusts the sensitivity of the string. If the glider is light, then it will quickly follow the sidewards gust to be blown out as the string is. If the glider is heavy, then it takes much more force for the air to move the glider, so the string will deflect a little more. Of course, when you're heavy, you tend to fly faster, and this gives the glider more rigidity, but the string deflection will be less and for a shorter period of time. So here, flying at 80 knots, get half a second of warning of the string. If you're flying slower, you'll probably get a 1 second of warning of the string. So here we have the LS6. Notice there's a little bit of turbulence as we enter a column thermal. The string is relatively steady and it's just sitting a little bit right of my word string theory. We're entering the column thermal. There's a vertical wind holding us up, and then eventually, shortly after the warning of airspace, you'll see the string shift. There it goes. Conventional centering for a weak thermal with a vario peak. Increasing bank, the right wing lifts and the string pushed left, therefore turn right with tightening the turn until a maximum turn is achieved. Of course, we could hit the thermal head on. No point waiting all day for the string to deflect, because it won't. So after the gust on the airspeed indicator, and certainly if you're going at speed, you need to pull up at that point. When the vario has been giving an increasing climb for 3 seconds, it's time to turn using full rudder and aileron. It does not matter which way you turn, so long as you turn. You anchor the wingtip at that point and only slacken off after 180 degrees of turn. Lift distribution cruising through weak and strong thermals. Only the depth varies. Here's my 6-knot thermal distribution. Here's my 9-knot thermal distribution. And we can see that to turn even tighter in the red circle, there's a benefit in the very strong thermals. So here we are at 50 knots and 60 degrees angular bank. And that's exactly what we have here. Do thermals rotate? Whilst heat causes both thermals and dust devils, the mechanisms are not complementary. For clarification then, thermals do not rotate. And if you thought they did, have you ever seen any evidence? Consider just 10 knots of rotation. As we pass through the middle, if the glider is flying at 40 knots, the left wing would be at 50 knots and the right wing would be at 30 knots with the same angle of attack. It would give us significant roll. Equally, the rudder and fin would be in a very strong crosswind, and so the glider would yaw. If we're turning then, a lot of aileron would be required into the turn to stop any roll. If we're going with the rotation of the thermal, a lot of outturn would be required to stop the roll. And also consider our turn radii. So if we're flying at 50 knots with 10 knots behind us, we would now have a true airspeed effectively, or true ground speed relative to the thermal, of 60 knots, giving us a 97-meter radius of turn. If we're flying against the wind of rotation, then it would be significantly reduced down to 40 meters. So when we look at a trace then, we'd be able to see the normal radii of thermals, and if we were rotating with the rotating wind, we'd have huge turns. If we're turning against the rotating wind, we'd have tiny turns. I have never seen a trace that indicates the above yet. Feel. Feel is probably one of the most important qualities we have to be a good glider pilot. What are we able to feel? Well, every bit of turbulence is caused by the interaction of rising and falling air. We feel accelerations, changes of speed, changes of rate of climb and descent. We can feel changes in rates of rotation, especially in roll. We feel changes in rates of acceleration and changes on lateral motion, the glider being pushed left and right. So what are we unable to feel? Well, we're unable to feel any motion where it is stable. So if we go in a lift, for example, of a high-rise building, we can feel the lift accelerate, but once it's achieved a steady speed, we are unaware. We have no sense of feeling that the lift is actually going up until it gets to the top, when it slows down, and then we have arrived. So when we are at a steady speed with a steady rate of climb or descent or a steady rate of rotation, we cannot sense it. Feel. So this is what we are feeling for apart from the three axes of motion. Do not over-control. We feel and hear on the audio the sink. We feel the cobblestones. We hear and see the speed increase. We feel the vertical surge. We hear the audio vario going up. We see the string deflection and feel the wing lift. We hear and see the speed decrease. Again, we feel the cobblestones and feel and hear on the audio the sink. Note that in a banked attitude, the relationship to the horizon has changed. Feel in the turn then. We feel and hear the audio on the lift. We hear and see the speed increase. We see the string deflection and feel the wing lift. We feel and hear vertical surges. We hear the change in audio vario up. We feel the tail go up or the nose yawing down. We hear and see the speed decrease. We hear the audio lift reducing, and if we fall out of the thermal, we feel the sink. Downwind wandering thermals. Cloud is history. If you observe some larger thermal clouds, it appears that the cloud and thermal base is moving downwind, away from its original source. This seems wrong, but it can be explained because it often does happen. They are known as column thermals, and cloud shadow and sink will be a significant contributor. A variety of thermal strengths may be found within a column thermal, just as you experience them routing down a street. Thermal structures. Consider first a column of warmer bubbles of rising air. It often starts with a heat source which heats the air and then rises, forming a vortex. The surrounding air will act as an insulator as the warm air expands, but is further restricted at the edges with the surrounding cool sinking air. If the thermal is stronger, it will appear narrower. Therefore, the stronger the thermal, the tighter you must turn. The turn radius is the important factor. It is achieved either at high speeds with high angles of bank or slow speeds and less angle of bank. Here we have a thermal structure with no wind. At the bottom then we have a heat source and the vortices are rising up. If it becomes a more unstable layer, the thermal lift will accelerate upwards, and so the thermal will appear narrower. If it broadens with height, well then the lift will weaken a little bit, and then eventually the cloud will form, and that cloud will generate sink around the whole column of vortices. If it continues to grow and the cloud continues to grow, We have a combination of many thermals, strong, moderate, weak, all rising air and providing humidity up to form the big cloud. The cloud then evaporates, making our tube of sink. And effectively we've got a rotation like that. And you saw that in the previous film of string theory. Here we can see a string of vortices coming off from a cooling tower. It's not a steady straight line stream of air rising up. Notice the broadening and narrowing with height. Nil wind, therefore a simple column thermal is being generated, with the evaporating cloud on the edge coming down, holding the whole structure together. Lapse rates. The adiabatic lapse rate is simply the rate of change of temperature with height. For moist air, the rate is 3 degrees per 1,000 feet. In simplistic terms, this is the air from the ground up to cloud base. For dry air, the rate is 2 degrees per 1,000 feet. In simplistic terms, this is the air above cloud base. The actual lapse rate is called the environmental lapse rate, which, amongst other things, can vary within or beyond these two rates, whilst humidity can also vary. So here we have our height on the left, from ground level up to 4,000 feet. And we're saying that the temperature on the left here is the environmental temperature, changing at 2.5 degrees per 1,000 feet. So in this case, the source warms up to 19 degrees. As that air rises, it cools at 3 degrees a 1,000 feet. And so it continues to be unstable all the way up. In this case, the air descending then is going to be dry air. And we're going to make it completely dry air and say it's going to only warm at 2 degrees a 1,000 feet as it descends. So now as this air descends, we suddenly find it makes the air unstable, because each time it descends, it finds it's cooler than the environment, and so it continues to go down all the way down to the ground. Note, sinking air can accelerate downwards, and we can get sink slugs. This can reinforce a next thermal hotspot or kill potential thermals. Cloud suck. Finally, the thermal may accelerate upwards from cloud base because the rate of cooling of the air within the cloud is then only 1.5 degrees per 1,000 feet, 3 degrees C below cloud base, reinforced by the surrounding cold descending air. This is because the humid air above cloud base within the cloud gives out heat as the water vapor condenses, causing the air above to accelerate upwards and suck air drawn in from below upwards to the accelerating thermal above. The higher the cloud, the greater the suck. Cloud development shapes. In this particular case, we can see spread out has occurred. Large, wide areas of sink and small thermals of weak lift, although occasionally you can get strong lift, but generally it's weak lift because the sun's not getting through. The cloud is unable to penetrate high into the atmosphere because it is stable, so the air rising up will spread out and form a complete blanket of cloud. Consider what happens with the cross-section of a thermal is likely to be rather than just up and down. if we consider for simplicity that a 1 degree temperature difference equates to 1 knot of lift or sink. So in the top here, we've got a conventional thermal 200 meters wide of rising air and surrounded by a band 40 meters wide of sinking air. Of course, that sinking air is colder than the rising air, but it may even be colder than the environmental air. So when you look at the bottom diagram, we can see that cold air coming down at -3 is considerably colder than the environmental air, and as a result the air next to it is then triggered to climb because it feels it's got certainly one side of it is what is colder than it is. And here we have false cumulus. So there's a big cell top right, and the cold air is cascading down the edge, and on the edge is forming these very weak, ragged looking cumulus. Thermal bubbles can be quite adjacent, indicated by this close but scattered pattern, and yet next to a bigger, better thermal. Cloud patterns are important because they tell you the current structure of the air underneath. These bubbles clearly had little vertical development, and there was no column development, and are quite likely to be false thermals generated by the instability and sink generated from the bigger ground-triggered thermal. The laying down of sink. While sink does fall straight down, it is affected by the wind shear at the lower levels. So, in the top half of this, the sink is coming down and the wind speed at 2,000 feet, say, is 20 knots. Much lower down, however, the wind is 10 knots, being slowed by surface friction. And that can trigger little cells on the downwind side of the sink. Shadow. Bearing in mind that a temperature difference of just a couple of degrees may produce a thermal, but the difference between in the sun and in the shade can be more than this, then it can be appreciated that the structure of thermals and sink will be continuously changing, and even regions considered strong thermal producing areas can be switched off by cloud shadow. So in this diagram then, we can see bottom left the wind direction and the sun angle. And so bottom left, a cloud has formed. That cloud forms a shadow in its 2 o'clock position. But when that cloud evaporates, it also makes a sink slug, cold air cascading down, and if it goes down to the lowest levels, that red area that we might look down and consider as being quite active and a good thermal generator is not. However, that cold air has generated a hot and cold disparity at Lunnington. That therefore generates a trigger for a new thermal which forms a cloud, which subsequently makes a shadow and an evaporated cloud sinkhole. And similar picture in the top half of this diagram. Summary then. String theory. Do thermals rotate? No. Feel the invisible sink flows.